In this separations video, I'll talk about how you would derive the equation for operating lines in the distillation column. This is going to be very similar to the process of single stage distillation, but you might have noticed that I use the plural lines for a distillation column. That is because we'll have, in general, 2 and 3, if you count them in a certain way, operating lines on a distillation column instead of just one, because there are 2 different sections of the column. And then you can also classify the feed stage as its own section of the column. So there'll be a different operating line for each one of those. So in a previous video, I had shown you how you would go through and solve all these equations algebraically. And I mentioned in that video that it was possible, yet it was pretty tedious and very repetitive. So once again, solving these graphically will greatly speed up our process. If you notice that our equilibrium relationships can always be solved with the alpha equation if we have an alpha. So just real quickly to start, remember that an operating line is a description of all possible material balances. And the other half of solving these problems is satisfying the equilibrium relationships. So you can generalize the equilibrium equation with the alpha equation. So y sub n is equal to alpha times x sub n over 1 plus alpha minus 1 times x sub n. Notice that the subscripts are matching. So yn, xn, and xn, where little n here corresponds to the stage that you're talking about. And remember that all compositions get the subscript number of the stage that they originate from. So for example, if n is equal to 2, and we're talking about stage 2, you would replace this n with a 2 everywhere, and y2 would be equal to alpha x2 over 1 plus alpha minus 1 times x2, for example. And this will always be true no matter what. So this reflects the fact that exiting streams from a stage are in equilibrium. So to that end, when we're generating our graphical solution, the first step involves plotting this alpha curve. So whatever your value of alpha is, you can plot y versus x, plugging in that one parameter. It's a little bit more difficult if you don't have a value of the constant relative volatility alpha, but hopefully in that situation you can plot y versus x regardless. So plotting your equilibrium relationship should always be the first step whenever you're solving a distillation column graphically. So let's start by deriving the first operating line, which is that of a rectifying section. Remember that the rectifying section is the top of a column. So here is just a process flow diagram of just the top section of a column. Note my notation here. So I can generalize this, and this is accurate whether or not, no matter how many stages I drew here. So I drew 3 arbitrarily. But no matter what, my L and my V are going to be okay without subscripts, because remember that L2 is equal to L3 because of the assumption of the constant molar overflow. And similarly, V3 is going to be equal to V4, so on and so forth. So I don't need subscripts on my liquid and vapor flow rates, but I do have subscripts on my purities. So I'm going to call x sub n the purity of the stream coming from whatever stage is on the bottom of the rectifying section, and y of sub n plus 1 coming from the stage below. So if I draw a process envelope and encapsulate everything going on in the rectifying section in this line, then I can perform a material balance on the top section of the column. All right, so I can do a material balance. And looking at what's going in versus what's coming out, I have V is equal to L plus D. Okay, so that's my overall material balance. I can also do a component A material balance and say that V times yn plus 1 is equal to L times xn plus D times xd. So similar to the material balances that I drew for single stages. I'm taking what's coming in and equating that to what is coming out. Notice here that the second equation that I drew, the material balance, you can rearrange this to get it in y equals mx plus b form by solving for y as a function of x. So I'm going to do that step now. Solve yn plus 1 as a function of xn. So it doesn't look too difficult. All they have to do is divide through by v. So that's one step. Y of n plus 1 is equal to L over V times xn plus D over V times xd. And one more step that I can do to simplify this a little bit is to substitute in my overall material balance to get rid of some of the variables. Actually, I'm going to divide through by D. So this may seem like a bizarre step, but it is a step that will simplify things in the future. So Y of n plus 1 is equal to L over D over V over D xn plus D over D over V over D xd. It looks like I've made it more complicated, except I have to recall how I define the reflux ratio. So remember, I also have an L here. This is L naught, which is equal to L for any stage in the top of the column. I define the reflux ratio to be equal to L divided by D. So armed with that information, I can now, anytime I have an L over D, substitute in what the reflux ratio is. And also what I'm going to do here is also substitute V is equal to L plus D. So substitute V is equal to L plus D, and L over D is equal to R. And if I do both of these steps in one, so you can go ahead and do the algebra for yourself, Y of n plus 1 is equal to the reflux ratio over R plus 1 times xd plus 1 over R plus 1 times xd. And this is the equation of my operating line for the rectifying section. That is based on material balances, all possible combinations of Y of n plus 1 and xn that are possible by material balances. So you can go back in the example that I did in the last class period, and instead of using the material balances every time, you can use this exact equation, and you can plug it in, and you can use it and see how you can solve for, I think we were solving for Y of n plus 1 in that example. If you just plug in what xn is, and you know what xd is and r because the problem statement told you what they were, you could find Y of n plus 1 very easily that way. So let's go ahead and do the stripping section now. And maybe if you feel comfortable with doing this, you can try and do it on your own. So very similar idea here. I have a PFD of just the bottom section of the column. I'm going to draw a box around it and perform my material balances around this part of the box now. Now this is slightly changed because my L is now coming in. So my material balances look like so. Oh, also one more thing I want to note is that because the stripping section generally has different V's and L's than the rectifying section, we denote that with a little prime. So V prime and L prime are going to be the flow rates in the bottom part of the column, and that will propagate through. So this flow rate would be V prime as well. Where again, we can drop the subscript because as long as we're in the bottom part of the column, all vapor and liquid flow rates are going to be equal to one another. V prime and L prime are not equal to each other. V prime 7 is equal to V prime 6. That's what I mean. Material balances are going to be L prime is equal to V prime plus B. So once again, in is equal to out. And my component A material balance would look like L prime times xn minus 1 is equal to V prime times yn plus B times xb. Once again, we're going to solve this equation for yn to obtain yn is equal to L prime over V times xn minus 1 minus B over V prime, forgetting my primes, xb. And then to simplify this, I'm going to use the boil-up ratio. So remember, VB is equal to V prime over B. So a little bit of confusing notation. V sub B is the boil-up ratio. V prime is the vapor flow rate from each one of these streams, and B is the bottoms flow rate. So what do I need to do in order to simplify it in terms of the boil-up ratio? I need to divide through by B. Divide by B. And that is going to get me yn is equal to L prime over B over V prime over B. minus b over v prime over b xb. And I will need to substitute in then that L prime is equal to v prime plus b. All right, so, oops, and I also forgot my times xn minus 1 there. All right, so simplifying this gets me the equation for my operating line of the stripping section. Yn is equal to v prime over b is vb, so vb plus b over b is 1 over vb, xn minus 1 minus 1 over vb xb. This is called, once again, the stripping section operating line. Okay. Once you have these two operating lines, you can go ahead and plot them both on the same graph if you know what the reflux ratio and what the boil-up ratio is. Oftentimes, you can relate one to the other using material balances. So before we see an example of this, I just want to go through and derive the equation for the third operating line, which is not independent, but it's oftentimes easier to calculate than the other two. And that is the feed section operating line, or the feed stage operating line. Feed stage operating line. So this is just a PFD of only the feed stage. And remember, this is where the stripping section meets the rectifying section. So this is not going to be an independent line, as I've mentioned before, but it's going to be the link between them. So in order to solve what the feed stage operating line is, we need to know what the state of matter of the feed is. We need to know if it's a liquid or a vapor and whether or not it's saturated. So what I like to envision happening here is if we have a feed that is all saturated liquid, it's going to come in and go straight to the liquid side to combine with L to make L prime. In contrast, if it's a vapor, oops, I messed that up. If it's vapor, it's going to come into this feed stage and go straight up and go towards the vapor. Or if it's a combination of both, it can do that as well. So in order to start here, we need to define the lowercase letter q, and this is what I said before, is that we're using q for multiple things. So define little q as the thermal state of the feed. And we are going to say arbitrarily, well, not arbitrarily, there's a reason for it, but we won't get into it later, that if Q is equal to 1, then that corresponds to a saturated liquid. Saturated liquid feed. And if Q is equal to 0, that is going to be a saturated vapor feed. You can also have a Q value that is between 0 and 1. So if 0 is less than Q is less than 1, you have a mixture of both. Or your feed is in equilibrium, is another way you can think about it, of vapor and liquid. And you could also have Q is greater than 1, which would correspond to a subcooled liquid. Or you could have Q is less than 1, corresponding to a superheated vapor. Okay, so given these definitions, we can write a couple of material balances now. My material balance that I can write is going to be L is equal to L plus whatever value Q is times F. So once again, just check to make sure that it makes sense. So let's suppose that Q is equal to 1, corresponding to a saturated liquid. Then in that case, I'd have L coming out is equal to L plus F coming in, which makes sense. Similarly, if I have a saturated vapor feed, Q is going to be equal to 0. QF is going to cancel out, and I'm going to have L is equal to L prime, which makes sense. The other equation that I'll need is V is equal to V prime plus 1 minus Q times F. So pause the video real quick and go through the same exercise that I just did, just making sure and verifying that that makes sense to you. Now, my two rectifying section balances and my stripping section balances I'm going to write. So for my rectifying section, remember that I had this from before. Y of n plus 1 times v is equal to xn times L plus xd times d. That was on the top of the column. And my stripping section was y of n plus 1 times v prime equals xn times L prime minus xb times b. So I adjusted the subscripts just to make them match, but this should be matching with what I've had from before. Right, if I rearrange it to get them in the same format. Now in the course of deriving this, I'm going to subtract these two equations. So subtract them. And you will find that if I factor out y of n plus 1, I've got v minus v prime is equal to xn L minus L prime plus xd times d minus xb times b. And by my overall balance, I can take this lump, cancel it, and set it equal to z times f. So you should be able to prove that as well. Actually, wait, I messed it up. That should have been a plus because I subtracted the second equation. So that minus minus becomes a plus, and that is equal to z times f. Okay, next what I'm going to do is go through and solve for y of n plus 1, and then use my derivations up here for L prime and V prime. So once again, y n plus 1. Now using this equation, v minus v prime is equal to 1 minus q times f equals x sub n. L minus L prime is negative qf. And plus zf can stay. I've got a common f in all of these terms, so that can be canceled out. And if I divide through by 1 minus q, I obtain y of n plus 1 is equal to minus q over 1 minus q times xn plus z over 1 minus q. And I oftentimes write this as, multiplying through by a negative 1. So this is the form that you may see it written in the textbook. And that's once again just multiplying top and bottom by negative 1, and then that gets it into a form that's a little bit more elegant. All right, this is called the feed operating line. Okay, so that is the derivation of all the operating lines. In the last video for today, I'll take you through how you would plot those lines, and finally how you would go about solving a distillation problem stage by stage by stepping off the stages, is how it's commonly referred to. All right, I'll see you in the next video.